second part of chapter 15. Now, related to that, we are going to study now what are really the, let's say, the tools or instruments that we are going to use to measure either the atmospheric pressure or to measure the pressure of any fluid. The first thing that we are going to talk about is the barometer, which is comparing the pressure due to the atmosphere to the pressure due to the column of a fluid. Usually that fluid we use mercury, and there are many reasons to use mercury. Okay, there are at least 4 reasons to use the mercury. The first one is that it is visible. The second one, it has a high density, and this is the reason why we are using, mercury is like the column length or height is going to be small compared to the one if we are using alcohol or if we are using water. Number 3, mercury does not stick with the walls of the the glass tube here. Then is going to be the values, they're going to be more accurate. Number 4, it's going to be the one that is talking about the boiling point and the I will say the freezing point of mercury. Now, this is going to be your exit ticket for this chapter 15. You're going to answer a question says why we are using mercury mainly in barometers, or like most of the things that we are going to measure. Usually we are using mercury. Why mercury? Why not any other liquid? And of course, this is going to be your exit ticket. You need to talk about the 4 points that I was talking to you about during this video. Okay? Now, all right. And as we can see here, there is a vacuum here. Usually we don't have, even like vapors, they're going to be, they are going to be low. They don't have like any pressure that we can, consider. It's going to be ignored. And then here I will say the atmospheric pressure should equal the pressure from the fluid, which is rho GH. Usually here we start using a unit called centimeters mercury, and this is, as I said, a unit, or we can say it is 760 millimeters mercury. Okay, now I will say this is developed by Torricelli, and that vacuum, sometimes we call it Torricelli vacuum. Measure atmospheric pressure. Diet of the column at sea level is going to be 76. Okay. Now, what if you filled this with water? Is going to be 10.3 meters. And this is why vacuum pumps could never lift water more than, about like 10 meters in, height. Now, also, we will solve one problem during the lecture if we are going to use alcohol. This is the second thing that we use for measuring pressure, and it is called manometer. And it is here, I will say, I need maybe to add pages here just to show you how we are going to deal with manometers. Usually we use, as I said, maybe we use, I call it J-tube. And then here, if I have this like fluid A, and that fluid A is pushing in a way that this is going to be the case. Now, how can I calculate the pressure of that fluid A? Now, we know that at this point here, the pressure at 2 points at the same level, it is equal. Then the pressure A here, okay, let's say here X and Y. then I will say here Px equals Py. Now Py, it is the atmospheric pressure. Now Px is going to be the pressure from the fluid plus that fluid here pressure, which is rho GH. This is my H here. And then the pressure of A here is going to be the atmospheric pressure minus rho GH. In this case here, my fluid has more pressure than the atmospheric pressure. Now let's assume here I have another scenario where I have this is B and I have here the pressure is, or like, you know, the levels are this way. Now here again I have this is my H, right? And I can say that again this is my XY equal to pressure Y. Pressure X, it is just the pressure from the fluid, and the pressure on Y is going to be the rho GH. Now this is the new H plus the P atmospheric. Then in this case here, the pressure of that fluid B is more than the atmospheric pressure. Now let's try do a kind of application. In a movie, Tarzan evades his captors by hiding underwater for many minutes while breathing through a long, thin reed. Assuming the maximum pressure difference his lungs can manage and still breathe is 85 millimeters mercury. Calculate the deepest he could have been. Then this is the difference in pressure equals 85 millimeters mercury. I like to convert that into, you know, for me, like always, I like to convert this into, you know, pascals. Okay, I did not calculate my number because I know that that difference in pressure should equal rho times G times H. Okay, my objective was from doing this is that I want to cancel some of the quantities. Then I cancel 9.8 from both sides. I'm using here mercury, then it is 13.6, like the density for mercury. This is like, this should be given. Okay, then I will say this is rho of mercury. It is 3 kilograms per cubic meter. This is cubic, not square. And from that, I can get that the depth is going to be 1.156 or 1.2 meters. There is another one related to the barometer. I want to move it here. Okay, I want to, you know, there are two of the problems that I think their position, they are misplaced. Okay, let me have them here. And then I'm going to move to, yeah, what did I do? Yeah, okay. These, I want to have them after Tarzan. This one first, and that one after. Oh. Yes. All right. Then now this was my problem, and then now I'm gonna do this one here. Water and then oil, which don't mix. Okay, then, and of course the density of oil is less than the density of water, and this is the reason why it will float. Are poured into a U-shaped tube, open at both ends. They come to equilibrium as shown in the figure. D1 is 27.2 centimeters and D2 is 9.41 centimeter, what is the density of the oil. Okay, and of course here, as I did with the manometer, I said like here the pressure of A should equal the pressure of B. Any 2 points on the same level, they are gonna have the same pressure. Then here I will say P atmospheric, the pressure from the atmosphere, plus rho GH on side A should equals P atmospheric plus rho GH on side B. I can cancel the atmospheric pressure from both sides. Now for the oil, it's gonna be rho oil times G times D1. For the water pressure is gonna be rho water times G times D1 minus D2. And then here I will say I can cancel G, and then I can have rho oil as 654 kilograms per cubic meters. Of course here, just I told you before, pay attention to your units. Maybe here it's gonna cancel, but sometimes it will not cancel. And of course here, always, whenever we are saying that this is just water, then we know that this is the density that is used for water. Another problem related here to the barometer: how high would the level be in an alcohol barometer at normal atmospheric pressure? I did calculate here what is really the pressure when I have alcohol. It's going to be 0.76 times G times 13, 600. This is the density of pressure. You can equally use P0101 10 to 5. And that equals the density of alcohol, the one that I'm using, times 9.8 times H. Of course, again, G is going to cancel from both. And when I will run the calculation, H is going to be 12.8 meters. Also, we still with statics, and there is a principle that is really very important, Pascal's principle, that is if I'm adding an extra force, creating extra pressure applied to an enclosed fluid, where we will find that is going to be unchanged, transmitted unchanged to every point within the fluid. This is really very important when we talk about hydraulic jacks, when we are talking about a brake system in a car. These are really very important. This one should go here, buoyancy. Okay, then that one also is gonna be all right. Then this is really here we are talking about that extra pressure that is added is gonna be of course going to the equation that we are we are going to discuss now. Okay, and now I will show you how I'm gonna derive the the equation here. Okay, now we know that the pressure that is created on the left hand side is gonna be the same as the pressure on the other side. All right. Now the pressure has to do with the force divided by area on the left, and the force divided by the pressure, the area on the right. Now I can say here then that if I want to find what VF out is going to be A out divided by AN times FN. Then here I call this force multiplier, and this is gonna make, like, if I will make in now the ratio between A out and AN very big, then I can multiply my force that I exert by by a considerable factor. And this is very important. As I said, like, you will go to the mechanics shop, then the worker is gonna just push the button, and he or she will be able to lift, like, with 200 pounds, could lift maybe 4,000 pound car. It depends, okay? Now, the next topic here, also related to static, is Archimedes' principle and buoyancy. Okay, now Archimedes was able to, go into a dilemma of, just like the king, the legend is saying that the king was trying to find if his a crown is made up of pure gold, and then he was asking Archimedes to do that without doing any kind of ruining for the crown. And then Archimedes was able to find a way that he is able to actually to find out what is the density of an object using physics. Now, we know that whenever you have a fluid that, we have, let's say, an object that is really inside a fluid, the fluid will exert a force upward on any object. That is, we call it the buoyant force. Okay, this force is due to the increased pressure at the bottom of the object compared to the top. There is a difference in pressure. That force, because of and that force, we call it buoyancy. That buoyancy, it has to do with the weight of the fluid displaced, okay, which is, here I have a cube, then it is rho times g times L cube, but in general I will say this is rho times g times the volume of the object. This is not V0. This is the volume of the object. Now, there is like two things related to Archimedes. It is when the object is just, I will say, like immersed, or if it is floating. When it is completely immersed or submerged in a fluid, it will experience an upward buoyant force that is equal in magnitude to the weight of the fluid displaced by the object. And this is the reason why I will say we have the weight in air, let's say a number which is mg. We have a weight in the fluid, which is usually, let's say water, is going to be less. Is going to be mg minus buoyancy, because the object is having that force, which is mg here, and it has a buoyancy upward. And of course, if I want to measure this, is we call it like the reading of the scale is going to be mg minus b. An object floats when it displaces an amount of fluid equal to its weight. And then here we are going to say that we are going to have that situation when mg is going to equal to buoyancy. Okay? An object made of material that is denser than water can float only if it has indentations for or pockets of air that make the average density less than that of water, is making like, you know, more volume. We can here use that equation, and finally, like this is the equation for the floating submerged volume submerged over the total volume. Okay, let's say volume equals rho for the rho for the object, let's say object here, divided by the raw liquid or fluid. Okay, here I want to solve problems related to buoyancy and Archimedes. Now, a crane lifts the 18,000 kilogram steel hull of a ship out of the water. Determine the following: the tension in the crane's cable when the hull is submerged in the water, and the tension when the hull is completely out of the water. Remember, this is maybe like looking like a simple problem here, but it is very important when engineers are designing, are using these different cables. They are going to use the information that we are going to get, because they should choose a cable that is going to capable of providing the correct, I will say the suitable, let's say, force or the enough force without breaking. Here we have, when it is submerged, as I said, we have buoyancy upward, mg down, and we have the tension upward. And we know that this object is in equilibrium. Then sigma F equals 0, and I can say B, buoyancy plus tension minus mg should equal 0. And then T equals mg minus buoyancy. And buoyancy, as I did say before, it is mass of the fluid times G, mass of the water times G, which is rho of the fluid times the object's volume times G. Okay, using that equation, I can say T equals mg minus buoyancy, and I was able to find that this is 1.5 10 to 5 newtons. Now, when the hull is completely out of water, B is going to be 0, and then the tension should equals mg, which is 1.8 10 to 5 in newtons. And this is really what is, we need to pay attention. Now we have more force, then we should pay attention to that when we design that system. This one here, we have a scuba diver, and her gear displays a volume of 65 liters and have a total mass of 68 kilograms. Assume the density of seawater is 1.025, 10 to 3 kilograms per cubic meter. What is the buoyant force on the diver in seawater, and will the diver sink or float? Okay, here, in order to calculate buoyancy, we know it is the rho for the fluid times G times volume of the object. I did here do this. Just here, I want you to pay attention to that I have converted the liters into meters cubed by multiplying by 10 to minus 3. Then I was able to get 653 in newtons. Now, here for part B, okay, this was A, this is B. I have calculated sigma F, which is the weight is downward and buoyancy is up. And then I have, now the weight is winning, then it will sink. I did mg greater than B. If B is equal to mg or more, this is gonna be floating. Okay, now or you can calculate the density of the diver by dividing the mass of the diver by the volume. you're gonna get a density that it is 1046, which is more than the density of the seawater. Then this means that is gonna sink. Okay, this one here also related to buoyancy. 5.25 kilogram piece of wood equal density equals 500 kilograms per cubic meter, floats on water. What minimum mass of lead hung from the wood by string will cause it to sink? I calculated first like the buoyancy, and I know that I have an unknown that is m. Here the volume, it is the volume of the two, and I will say it is mass divided by density. And then I know that m total is gonna be 5.25 plus the mass times g. I have an equation with m in it, and then is the only unknown. Then I have collected my terms, and I have calculated my mass to be 5.76. All right, this I'm gonna stop here because in the coming part I will have like I will talk about fluids in motion. Okay, and here it's the end of fluids statics. Thank you, and see and meet with you soon.